Wachiku, and this is Physics 2211, Lab 4, Oscillations. Okay, here's our table of contents. First, we'll go through introductions, then to fundamental principles, then to tracker data, then to glow script data, then to the data analysis and conclusions, and then further questions. Okay, for introduction, the purpose of this lab is to investigate the motion of the spring mass system with the mass oscillating in an arc in the y and x hat the y hat and x hat directions using tracker and glow script data. The goal is to determine whether models follow the energy principle. The system would be the mass spring in the Earth, and because of that, the surroundings will be nothing. The observed positions will be found using tracker, and the predicted position will be found using glow script. A brief preview of the results is that the change in total energy is 0, and the predicted and observed models are similar. Here's our fundamental principles. Newton's second law, of course, the acceleration of the object is proportional to the net force acting on the object and inversely proportional to the mass. The energy principle, which says a system's change in energy is a sum of the work done by its surroundings and thermal energy exchanged with its surroundings. Here are the energy equations. Delta E equals W, which is the change in energy equals work, and the change in energy also equals the change in kinetic energy plus the potential gravitational potential energy in spring force potential energy. We also need to use the velocity update formula, which says Vf equals Vi plus F net over m times delta t. And the position update formula, which is the final position equals the initial position plus the average velocity times the change in time. And then the force due to gravity, which is negative mg in the y direction. And the gravity equals 9.81 meters per second. And the spring force, which is Fs equals negative Ks L minus L naught times L hat. And then the kinetic energy, which is 1/2 mv squared. The gravitational potential energy, which is mg delta h, or delta y. The spring potential energy, which is 1/2 ks, the absolute value of L minus L naught squared. Some key assumptions that we also need to know for the lab are that the major force acting on the object is the force of spring and the force of gravity. Drag is negligible and part of the model, and the object is only moving in the x and y directions. The origin is at the attachment point of the spring. Okay, and then we're going to go into our tracker. Here's the data that I got here's the video. All right, here are the initial conditions. The ball's mass is 0.402. The position is there, and the velocity. And then a computational model, the rest of it. These are just some important things that you need to know. The gravitational force, the spring constant, the relaxed length. Here you have the kinetic energy equation, the gravitational potential energy equation, and the spring potential energy equation, and then total energy. The force of gravity is here again. The force of spring equation is used here, and then you get the net force, and then from that you can use the velocity update, position update, and get everything else that you need. Here are results. Look at the legend to see the delta K, delta E grav, delta U spring, delta E, and you can see that the change in energy is basically 0. Here's 2 graphs of the observed versus position or predicted positions. You can see the model versus the experiment here. Okay, what does this all mean though? Is the energy principle satisfied? There is no work being done by the surroundings on the system, so the energy principle is satisfied. There is no gain or loss of energy, so energy is conserved. Delta, or the change in energy in the system, equals the work of the surroundings plus Q equals 0. The oscillation period for the x position of the graph is close to t equals 1.614. And then the oscillation period for the y position of the graph is close to t equals 1.487. The period is different depending on the direction you choose. All right, that's all. Thank you.